Let's wrap up with some comments on finance, which is pretty difficult. This is a very big topic. So finance is covered in business schools and economics departments, mathematics departments, operations research departments, sometimes statistics or physics departments. So everyone kind of has their take. If I'm going to recommend a book, this is by far number one on my list. Donald Mackenzie's An Engine, Not a Camera: How Financial Models Shape Markets. So this is not a math book by any means, but it does talk about the models, but moreover it talks about figures and people who developed these models from the 18th century to now. So there are a number of characters that appear in the book, which is what makes it interesting. So one of them is Jules Renault. He's a French broker and kind of an amateur mathematician who came up with perhaps the very first mathematical model for stock price movements. There's Louis Bachelier, who's perhaps the originator of mathematical finance as we know it today. He's also often credited with the invention of the Brownian motion, although some would disagree. Edward Thorpe, a mathematician and a gambler who worked in finance after gambling became a little bit too dangerous for him. I think he was poisoned at a poker table or a blackjack table at some point. Paul Samuelson is an MIT economist who is widely credited with the geometric Brownian motion model for the stock price, which is still widely used today. There's Matthew Osborne, is a physicist who may have actually been the first one to come up with the geometric Brownian motion model for a stock price. And then finally Mandelbrot, after the fractals and the Mandelbrot set, he was interestingly one of the most vocal critics of the geometric Brownian motion model, and proposed alternatives, including something called the fractal Brownian motion. In any case, I really could not recommend the book more highly. It is certainly going to set you on the right path if you want to work on this area within academia or in industry. In any case, the geometric Brownian motion was mentioned quite a few times. Black-Scholes, yeah, it is part of the Black-Scholes model, and both Black and Scholes are covered in the book as well. So I want to kind of point out a few differences. This is what we usually think of as the model of the price of a stock. I think I skipped way too far ahead. Okay, so I mean to be here. So this is the model, the geometric Brownian motion model for the price of a stock. There are a number of differences from Ross, who curiously decides to omit this term right here, the sigma squared over 2. I'm not sure why, but the terms are important, and I'll show you why they're important. So the interpretation of the model is that of a random walk on a logarithmic scale. So in other words, the logarithm of the price follows a random walk, and another way to say it is the returns are log normal. So there are these two parameters that are involved in the definition of the geometric Brownian motion, or the price of a stock, sigma and mu. So mu is often thought of as the return, and sigma is thought of as the volatility, the uncertainty in the return. So if you look up the S&P 500, the most important index for US equities, this would roughly translate to a roughly 9% return annually. So $1 at the beginning of the year grows to a 9% return at the end. And the volatility, the uncertainty around that is 16%. So I made a few simulations here of this process. So starting from some price, I simulated a bunch of trajectories using these numbers here as parameters. Here's a little bit of code. So right here you can see that the mu, the return, is set to be 0.09. That corresponds to my 9%. And the volatility is 16%, so 0.16. And so if we were to compare that with something coming out of Google quotes, this is the Google chart for the S&P 500. starts at around 121 bucks in 1981, and in the next 40 years grows up almost, it's still short of 5,000, but on the way. And this is a simulated trajectory, which is roughly comparable in terms of the numbers. So out of the ones that I picked, I think it looks like I picked this one because it kind of matches the numbers well, but in others there's a different type of behavior possible. This looks like a pretty big financial crisis right there. Okay, so when thinking of kind of working with data, right, empirical work, you're often computing return. So this is the formula for the simple and the log return. This link goes into the differences as to why you'd use one or the other. They're roughly going to be the same for most practical purposes, but simple return is just the price at the end period minus the price initially divided by the initial price. So it's price change over the starting price. So it gives you that how much your investment grows in that period. Log return is similar. And what I want to do is convince you why the names that I quoted here, why mu, the parameter mu, is called the return, and why sigma, the second parameter of the geometric Brownian motion, why that's referred to as the volatility. So what we're going to do is run through some simple calculations. I'm going to start with the simple return, and we're going to apply a Taylor expansion of the second order. You'll see why the second order is important. We're going to aim to keep terms that are of order h. So we have a little bit of a window of time, right? So the price is changing in a window of size h. T is the current time, and then we're looking at the closing price at t plus h units from now. And so this is the return over a period of time h, starting at time t. We're going to try to keep things that are of order h and pretend that things of order h squared are small. And so for this reason, I've expanded only up to the second order so that we don't omit anything. So there's going to be a little bit of an interesting thing that happens with this Brownian increment, as you'll see, I think, on the second slide. But for now, one thing we can see is that this component of the return is on expectation 0. The Brownian increment has a 0 expectation. And so you can see how when I do take the expectation of both sides, I lose one of the three terms, ending up with just two. One that's linear in h, and another one that so far seems to be quadratic in h. And so maybe it's okay to omit it, but for now I want to try to actually take that expectation. So we're right here at this equation. We're going to look at the quadratic term and see if anything there that's of order h can be extracted. So we're going to factor out this quadratic. This is this is a term of order h squared corresponding to this part of the formula. The leading term here is actually going to be the last term, the Brownian increment squared, and this is the cross term. So the cross term is not important because, again, the expectation of the Brownian increment is 0. We ignore that. However, the squared Brownian increment is actually its variance, which we know to be of size h. And so we were wise in keeping the Taylor expansion on this slide up to the second order. So in other words, the second order Taylor expansion is needed to capture all of the terms that are of size h. So what do we get? We get rid of the cross term, we get rid of the term that's of order h squared, and now it's just a matter of adding the contribution of the Brownian increment squared and this linear part of the formula. And what you see is that they actually cancel out nicely, which is the reason I had an objection to what Ross does in the textbook. That kind of kills the interpretation of mu as being the return, because in this formulation, what we actually obtain is the approximation for the expected return to be mu h. In other words, mu is kind of an instantaneous return. So if you want to get the return for h time units, you just multiply it by mu. And this formula, in fact, becomes exact if you take h down to 0. So that's what I've done on this side. And so for small windows of time, we can kind of justifiably attribute the return to this parameter mu. And we're going to look now at what we do kind of with empirical data. And so say you have a time series of stock prices, maybe it's the S&P 500, which you can download from Yahoo Finance. If you now if you want to approximate the return of that time series, in fact, any time series, this is the kind of calculation you want to do. You have n periods of time, and you average the return, and you'll get the historical return for that time series. And then what I mentioned here, besides that, is kind of different conversions and different conventions around quoting the return. So in U.S. equity, it's often that you quote the return in annual units, so annualized numbers, which would be true if time here was of a unit of 1 year. But now if you want to do some kind of quantitative work, you often work with higher frequencies. So daily data, weekly, monthly data, even quarterly data. And so you need to kind of have a way to translate to annualized return. So that's what I've done for you here, at least in terms of daily data. This is how that conversion would work. You're looking at investing with a daily return, and you're going to do so over the course of the year, which is what explains this power here. 256 is the number of trading days in a given year. And so what you're doing in this part of the formula is saying that we're going to keep reinvesting all of the earnings from an initial investment of $1 for 252 days, and then we're going to subtract the initial investment off to just capture the return on the investment. And so this is approximated by, for a small daily return, which it typically is, by just this multiplication. So 252 times the daily return gives you the right quotable units of annual return. And now, let's see, we can do the same thing for what would be called the volatility. The volatility would be the square root of the variance of the return. So that's what I'm trying to compute here. And you can do this with the same Taylor expansion approach that we used before. So this is my Taylor expansion up to second order. And if you track it, what you'll essentially see is that the only contributor to something that is of order h, which we care about, is really going to be this term alone. This is going to be squared because we're taking the variance, and then here you're going to see terms of size, h to the 3 over 2, but these things are small relative to something of size h. And so I'm going to keep just the Brownian increment squared, in other words, the variance of the Brownian increment, and then I'm going to take the square root to get the deviation, and that's going to lead me to this result here. So in other words, units of volatility go in time lengths not linear in h, but square root of h. And so you can see now why sigma, this parameter of the geometric Brownian motion, is actually called the volatility. It satisfies this equation as h goes to 0. And sigma is really kind of like an instantaneous volatility, and it needs to be scaled by the proper time interval on which this is happening. In fact, the square root of that time interval. And this is where the property of the Brownian motion increment becomes important. The fact that when you multiply the increment by a square root of h, the variance is then h. So let's see where we are. We can look at some empirical work again. This would be the formula for computing the volatility of a time series. And if you do this for S&P 500 data, you'll get roughly 16% in US equity. And now the square root business comes up again. So we've already seen this property of the Brownian motion. If I scale the Brownian motion W by the square root of t, I would get the realization of another Brownian motion at time t. And so this again covers conversion from daily to annualized volatility. So again, you often quote things in annualized terms and very frequently work in higher frequencies. So if you were to, for example, estimate the annualized volatility using yearly data, the S&P 500 has only been around for maybe 100 years, so you get 100 data points to work with. Whereas if you were to use daily data, obviously it gives you quite a bit more observations to work with, and then you just need to translate to annualized units, which you do with this square root of the number of trading days per year if you're going from daily data, and then obviously depending on the frequency you would adjust this. But the point is that you to annualize the return, you'd multiply by the length of the period, whereas if you want to annualize the volatility, you'd multiply by the square root of the number of time units in that period. So here 252 is the number of trading days in a year. Okay, so a good place to start with kind of these types of calculations and simple statistics is Yahoo. So Yahoo Finance provides historical prices not only for the S&P 500 but for many stocks in general. And a nice exercise is to actually carry out some of these calculations and see if you do get good estimates and what frequency is sufficient to get something of roughly the order of 16% in terms of volatility, and 9% for the annualized return. So I'm gonna skip ahead to some more advanced topics where I'm just gonna mention a few things for kind of those who are enthusiastic about math finance. All of this stuff gets terribly complicated terribly quickly. But I'll mention a few of the advanced topics that you want to have your eye on in case you want to study the area kind of more rigorously. So one thing that often comes up is what's called stochastic calculus or stochastic integration, which I'm going to build up to this expression in a second. But the way this starts is that suppose you're buying NTK units of a stock at time TK, and we're looking at how much profit you're going to make over n turns of this. So you're going to buy n times, and each time you're going to select n TK units to buy. And so this formula would write down the profit. Let's see how this works. If I buy n units of a stock, then I should multiply by the price to see how much money I've actually invested. And once I've invested some money, I can multiply that by the return, which we've already covered, to see how much profit I made. And now the upstairs cancels downstairs, and it reduces to this nice expression, which looks kind of like a Riemann integral. So in fact, it's a stochastic integral, but it looks like a Riemann sum to some extent, except that in Riemann sums, usually this term right here would be tk minus 1. Here we're using the price itself as the quote-unquote differential. And nevertheless, things work out relatively analogously. And if you do take the limit, this would be called continuous trading. So you're not trading over just n finite timestamps. You're kind of going to take the limit and continuously be trading in continuous time. This expression should converge to an integral. So if Tn, as n goes to infinity, approaches to t, that's the upper limit of the integral, and therefore the number of trades then goes to infinity, you would have the following integral for a continuous time trade, resulting in the profit at the horizon. Horizon is the kind of a reference to the final time at which the last trade is executed. And then there's a lot of theory that goes into defining this differential. How do we interpret it? When is it okay to use it? And so on and so forth. for the geometric Brownian motion, this is what the differential looks like. And it's the calculation that would show this is roughly comparable to what we did for the return. We saw that we computed the return and also the volatility, not just the return, but both of those calculations could be used to then maybe not rigorously, but as a sketch, prove that the differential or the change in S it would be equal to the change in time. That's the dt component. So how much the stock drifts based on its average return, and then also the how much the volatility swings are taking it in one or the other direction. And then furthermore, there are tools in stochastic calculus to actually show that this, which is this is a differential equation here. So what I'm highlighting in the box here is a stochastic differential equation. This part of it, without the Brownian motion, would be just an ordinary differential equation. But as soon as you add this Brownian term, it becomes a stochastic differential equation, and there are tools that can show you that you can solve it with this formula here. And so we're back at the definition of the geometric Brownian motion. Another very big theme in mathematical finance, at least, is the kind of the subject of pricing financial instruments or pricing financial contracts. And this is where the most important concept is called the risk neutral measure, which is covered by Ross a little bit, but I don't recommend you read that because it's just there's a limited amount that one can take away from that presentation there. So, in fact, you probably want to take an introductory class to math finance to get a little bit into this subject. But roughly speaking, the core probabilistic concept is the martingale, which we've seen. And so there are reasons for introducing it. This is really the core concept in the theory of stochastic processes, and also at the core of mathematical finance and pricing of various financial instruments. So you price instruments with respect to a martingale, and what you immediately will notice is that this process is not a martingale. We saw the plot of it. The plot of it went up and up and up on average. That's not what a martingale does. A martingale is something that stays even, right? It maybe has some deviations up and down, but in expectation it stays level. And so what you do when you price, you actually want to come up with a martingale, which in this case is going to involve a new stochastic process M, and also something complicated called a risk neutral measure, which is a set of probabilities that turn M into a martingale. So this is outside the scope of this class, but roughly what this is saying is that there is going to be some mu that gives an upward trajectory to the return of the original process, but everybody benefits from this return. And so if we're going to actually consider profit making or trading around this kind of slope, the mu itself is not that important. What's important are two things: a martingale process for the price, and also the risk-free rate, which is the guaranteed rate of return that has no risk associated with trading this particular instrument. And so with these kind of concepts, what you then come up with is what's called the risk-neutral valuation formula that can be used to price various instruments, including the call option. So we've seen an example of it where I took the easy way out and I said, let's model the stock price by a martingale. And that allowed me to give you a very quick, easy to motivate recipe for how to price the options. You can review that argument to see how the fact that this price was a martingale allowed me to argue for what the fair price of the instrument there was. One thing I ignored there was the interest rate. I in fact set it to 0 in that presentation. When it's not 0, you're going to discount the price by this discount factor, which kind of gives you the value today of something T units in the future. And in general, what you're going to do is set the price to be an expectation with respect to this Q, which is a risk neutral measure, which ensures that there is a martingale underlying the actual pricing process. So this E would come into this formula. It would then yield us a martingale with respect to which we can actually price. So don't worry if you're not following the details. The details are difficult, and you may not even understand it after taking your first intro to math finance class, but that's where you kind of just gotta persist a little bit. And what I will do to help is I'll introduce martingales in the context of gambling. Even though no one tells you this, financial markets are basically gambling, and pricing is simply a matter of understanding gambling odds. And so what I will do to kind of help prepare you for maybe potentially a future class in mathematical finance is to give you a little bit of background in martingales from the perspective of gambling. And so we'll do that in the next lecture. So see you then.